I'm here to talk about RX-SOP and what it is, how it works, and what challenges it addresses. So we'll go over some of the overview part, and then I'll hand over to John Blasco, who will go into a deep dive into exactly how this feature works. So this feature is mainly targeted towards the high density deployment. And some of the typical challenges at the high density is you have to get more APs into the smaller area so that you get a capacity, but then you have to address the problem like co-channel interference and other type of interference which are interfering with your system. So you eventually get down your capacity. So to make sure you don't do that, you have to make sure your RF or layer 1 RF environment is robust enough to provide the basic wireless, because that's the heart and soul of the wireless infrastructure, right? You have to get your layer 1 stuff to the perfect level. And then on top of that, you can add your above layer application like your voice or video communication or video streaming or UCC application. So those applications will fall apart if you don't have your basic layer 1 foundation right. So to get that foundation right, we have multiple ways to address that, like a proper selection of antenna, like internal, external, with directional patch antennas or stadium antennas. Then we have many other options like disabling lower data rate to shrink down the cell size. Then we have low RSSI check to further shrink down that. And then finally, we have this RX-SOP feature. So what is RX-SOP? It is the receiver start of packet. So in technical term, it's the sensitivity of AP's radio to either like hear those packets or ignore that. So basically imagine a Cisco AP with a earmuff. So it can basically tune its earmuff to whether hear particular type of packets, not particular, RSSI packets or ignore them. So this is the challenge is being addressed by RX-SOP. So how it works? So you have typical cellular architecture where you have multiple Wi-Fi cells, multiple APs. So over here I'm showing like in 2.4, multiple APs are on channel 1, 6, and 11. So you design this like that. But once you deploy that, you often see that your cell size is getting bigger and bigger because RF is not stopped by, not completely stopped by walls or any other material in between. They propagate through that material. So we are trying to reduce down that propagation out of our design cell boundary. So what we will expect is shrunken down cell size so that we can do a better reutilization of the spectrum so that we'll get more and more non-overlapping channel, and at the same time they are separated logically from each other. So get into the detail, I'll call up John Blasco. He's a technical leader and he will go into like detailed session about that.
Thank you, Kshitij. Again, I'm John Blasco. I'm a RF hardware / system engineer from the Richfield, Ohio area. So I want to lead with RX-SOP. It sounds kind of great and everything, and this is actually not new. This is not a new technology for Cisco. Cisco has been taking advantage of RX-SOP for a number of years now, particularly in high density locations. So I mean, we have a lot of history with this. We are opening the ability for users to adjust these SOP thresholds with newer software releases. But this is actually something we've been doing for years and years in stadium and high density deployments. So it's not new and as sexy as multi-user MIMO, but it's been around, and it applies to, I mean, everything from 802.11b up to 802.11ac. So. But first, I'd like to start out with a little bit about the channel access mechanism of 802.11 networks. It uses a carrier sense multiple access with collision avoidance architecture. And what that means is, should I really transmit a packet now? And how do I know when I transmit a packet? I mean, is there something, how do I know I'm not going to collide with somebody else? Wired networks have a collision detection mechanism because they're attached to different devices. But wireless does not have that. So before they actually transmit a packet, one mechanism they use to see if the channel is free is a physical CCA. And what the physical CCA is it actually goes out and it checks on air if there's any noise or any packets on air before it transmits. If the channel's free, it's free to it can transmit. Obviously, in conjunction with the virtual CCA, which is the second point. So there's also a virtual CCA where if a packet receives, or if an AP receives any packet from any device on its channel, it has the ability to decode how long that packet's going to be on the air and set its network allocation vector, its nav, to say, hey, I'm not going to transmit during this period of time while I know this packet's going to be on the air. So, and that's actually set by the sensitivity of the radio. If you have a radio with great sensitivity, or 11B radio is a great example of this because it has the best sensitivity of all the rates at 1 megabit. I mean, this is actually, I mean, you hear everything down to around minus 100 dBm for that rate. For OFDM rates, it's in the minus 90s for 6 megabit or M0, depending on what type of network you have. So you hear everything. I mean, you hear everybody's packet, and you hold off. You hold off transmitting for everybody's packet. And that's actually a problem in some networks. I mean, in older networks where we had larger deployment scenarios, it wasn't so much an issue. But as we shrink the network size, it becomes an issue. So key takeaway on the CCA items is that we have a physical and a virtual method. Virtual is set by the sensitivity. The physical CCA is actually set by a CCA threshold on the radio, which is kind of recommended by the IEEE. It's around minus 64, minus 65, I think, per the standard. So before it transmits, it's got to have an OK from both the physical and the virtual CCA mechanism. Now, a receiver started packet is more of, should I receive a packet? As a packet comes into a radio, it sees a bunch of energy and it immediately kicks up its AGC, it kicks up its decodability of the packet, or decode state machines for the packet. And it's quickly got to decide, based on what type of energy it sees and what level it is, hey, should I spend time trying to decode this whole packet? And the hardware today can control, should I decide to receive this packet based on the signal level that it's received at. So when we say, that's where the term startup packet comes from, it's, hey, is this really a startup packet or not? And we can determine whether we want to go through the time of decoding a packet, which for low data rates can be very long, based on the RSSI level of that packet. So basically, we have a channel access mechanism where we have ability to adjust when do we decide to transmit a packet, and should I even bother receiving that packet. And the next slide, I'm talking a little bit about kind of a basic slide here, but this is where we've been in the past for a lot of scenarios where we have a larger, I call it coverage area network, where an AP might be serving many clients, many cubicle farms is a good example of that. And we don't have a lot of frequencies at 2.4. This is scales for 5 gigahertz as well. But a lot of the deployment scenarios that we have been involved in over the years requires a higher megabit per square foot. And you can kind of see in this case, we're trying to almost jam almost an AP in every cubicle farm, or cube. And it kind of provides each user for its own personal cell. And stadium environments is a similar environment where we have a lot of APs that we have, and we don't have a lot of frequencies, and we have a lot of channel reuse problems where users, APs I should say, hear other APs and hold off. So this is kind of the summary of a side view of the problem that I'm trying to explain here. And maybe I should jump over here to the whiteboard and kind of draw it up a little bit here. Maybe I'll just kind of take it here. So we have a scenario here where we have an AP, say AP1, it's on a given channel, say 5180, and it has a power delay profile that I kind of shown up here, where its power level kind of rolls off in an exponential nature, right? There's in high density deployments, there's a co-channel AP at a distance, with a similar power delay profile. And often is the case, he's at 5180 as well, similar channel. And we have a client that may be associated to AP1 in this general area. Well, it often is the case, especially when you have closer in APs, where the client itself has enough signal to interfere to SNR or SINR, signal to noise or interference ratio, to decode a given packet at a given rate. However, this level that he's receiving from the other AP, this transmit power level, is above his starter packet, which would be, again, down in the low minus 100 range, or its CCA threshold. Sorry. In which case, he is actually sharing the channel, because this AP receives every packet that this guy transmits, and he is holding off for him. Although he could have, during that time, transmitted to this client right here during this time. So and again, if these guys were placed very far apart, this becomes less of a problem. It's in a normal, like a coverage density network. This isn't quite as much of an issue. But as you pull the clients together at co-channels, this becomes a big issue as we have this hold-off problem. So sufficient SINR for the client, but insufficient contention. We have a problem with contention with the APs. So I kind of try to draw this probably a better, more orderly way up here. But so we have the AP1 with its transmit profile and the AP2 with its transmit profile. And again, the client here has enough signal to interference ratio to decode the packet. However, the AP2 signal is above the physical CCA threshold that it would actually have to go out and check before it transmits, and the virtual CCA threshold. So it's a problem. We could have got that packet out, and we're not doing it. It's a throughput hit.
So is this, you mentioned the earmuff idea, is this changing the receive sensitivity of AP2?
It is. Well, yes.
Or is does it still have the same receive sensitivity, we just apply it after?
It's a good question. In hardware, there's different ways of doing this.
Yeah, that was my question. Yeah.
You could put an attenuator, in the front of the receive path, and that would affect every rate individually. That's not what we do. We want to, and that would shrink all the cells equally, right? Which you don't want to do. You want to keep the the data rates with the same rate, with the same cell size. You just want to shrink the boundary, right? So what we're doing is if it's like an absolute RSSI method, if it's above a certain RSSI level, hey, we decode it. If not, we ignore it.
So CCA usually listens. So you actually listen and then make a decision after you listen.
Correct. If it can't, so the SOP, if it can't hear the packet, it doesn't listen to bother to transmit. So we actually move these in sync. I'm just trying to draw out the difference between the CCA and the virtual method here. What
you're trying to do is get it to AP2 to stop deferring for someone in the next cell over.
The co-channel cell.
Yeah.
Yep. If it's an next cell and it's an adjacent cell, then it doesn't. He's not really sharing the channel. Yeah, he's not sharing the channel. So the key here is it's co-channel too, right? And a high density network where there's a lot of traffic. If this guy's not transmitting either, it's not a problem, obviously, right? But in a high usage network, it's a huge problem. So having more cells is key here, especially for high density. You want to have as many cells. You want to have as much channel reuse as you. A larger cluster size and move the similar channels as far apart as possible, so to minimize that. But even, as you start shrinking these cells, this problem becomes a problem.
So can you use this information and by setting that in doing a validation survey, coming back and adjusting your requirements?
You can.
So you used to say, if anything's above neg 85, I have a co-channel interference. Knowing that we can put SOP on, we might rev that up to 75 or whatever matches your SOP.
Yes, you could do that, but my next slide, I want to drive this other point home too. When you're setting up your cells, you still need to be careful about that. We're not, this next slide is meant to say, hey, we aren't breaking any laws of physics. We're not tearing down Shannon laws. We're not doing anything like that. We're actually just, we're trying to fix a hole with the scalability of the IEEE standard with scalable networks. If a client doesn't have the SINR to decode, we're not going to fix that. I mean, that's physics. I mean, that's not a problem. I mean, that's not a problem that XR receiver started packet's going to fix. So, I mean, when you're setting up your cell size, you still want to be careful when you're setting up your cells not to, I mean, if you want to guarantee a certain data rate.
I was saying when you report where do I have co-channel interference, you can now say I don't have co-channel interference because I...
Oh, you didn't hear it? Yeah. Okay, if you're saying from like a, hey, where is the interferer coming from?
As a report that says here's where I have co-channel interference, now I can adjust that.
That's true. Yeah, you will not detect it. And I mean, from a radio management standpoint, yeah, it won't show up. I mean, you're putting the wax in your ears, man. You're not hearing anything. I mean, beyond that level. So, sir?
I love this conversation, by the way.
Oh no, well, let's go out and have some beers and talk about it.
You know, it's funny because Keith and I had a call not long ago talking about something very similar to this.
Yeah.
So help educate me. So, you know, when before the frame goes out, a preamble goes out, right? And depending on if it's an OFDM preamble, it goes at 6.5. If it's long, it goes at 1.5. If it's short, it goes at 2.5. So those clients and radios, APs, clients will see that preamble. They would digest that preamble. And in the length field of that preamble, there's a set time that they will know that this frame is going to take to deliver.
Correct.
Now, the radio that's on the far end may not be able to distinguish when the actual frame is sent because it will pick up in phi. Those clients will typically do a EIFS, which is a longer time period of back off.
Correct.
So how does this work for the access point that's at the further end who can't understand that phi? Does he still honor the EIFS, or does he also ignore that?
No,
Did I explain it right?
Yeah, well, the standard protocol is going to hold. If you have an error packet, you're going to back off to your EIFS, and you're going to hold off a little bit more before you transmit another packet. That's not going to change. I mean, all we're doing is putting the wax in your ear, and if you set up the network in a way that it's not a problem, I mean, hopefully the APs are not interfering with other APs well, if you set your starter packets settings correctly, I mean, hopefully they're operating independently, and you don't have that problem as much. But we're not changing the protocol with any kind of error back off or anything like that.
I think to answer your question, this is happening at CCA. We haven't even decoded that preamble yet. We haven't looked at it. Yeah. We're listening and saying we heard it below this level, so we're going to ignore it, even though we could have decoded it.
Well, we're dropping it early too.
Yeah, you're dropping it.
Yeah, we're not spending time with it.
Yeah,
right? I mean,
that's not even happening then.
So it's not even happening. So this solves your question you had earlier because we just ignore it, whether or not we could have decoded it.
Gotcha. Thank you.
Now, in terms of like, there's another feature called low RSSI check. That just means the radio still decodes it. He just isn't going to respond if it's from a client perspective. He's not going to respond if it's below a certain threshold, or lower than a certain threshold.
I'm going to have to pass on that one. I don't know our lowest RSSI check, but we could catch up off base. I'm not familiar with that feature. Jeff?
Actually, am I supposed to fall into karaoke now? So I'm Jean-François, JF for short. I'm in charge of the software on the AP. And there's a new set of feature, or like family of feature package, and we call it the Smart Roam, that might go to the lower RSSI. And the idea, it leverages the RX-SOP and a bunch of other features. And the idea is one of the problems that people have is at the edge of the cell. My personal grief was in the past, you're on your phone, browsing, Cisco makes you work and do email until you're off the network. So you're in the parking lot, and you have to get on a WebEx call, like commuting home, and then you're in the parking lot and you're still on the Wi-Fi of the building, but you're like 60 feet there. So you have a really crummy signal, but the cell phone logic, because that's the problem. The client decides if I'm going to cell or Wi-Fi. And there's no CCX. We don't have an interface with the phone telling him, hey, Mr. Android, please go to cell mode. So we have that feature, which is basically you set up, and the EP is going to kind of measure your signal. RX-SOP is like that. Because one of the things is that your cell phone is going to have a transmit budget of 18 milliwatts, and the EP has 100 milliwatts. So the EP the client is hearing that now AP loud and clear, but I cannot hear back. Now I don't have a big microphone to blast the signal. So you have to kind of tell the mobile to go and beat it, like go on cell mode, stop being on the Wi-Fi. But there's no protocol. So leveraging CCX as CCX, RX-SOP, another feature, what we can do is that we basically have kind of two thresholds. The first threshold is I'm stop replying to you. I ignore what you're saying. And the other threshold, I'm getting you at the hot. So I see that as my analogy is like you go on a date with someone, coffee, 30 minutes. And within 5 minutes, it's not gonna work. Okay, so you go and you wait, you go back home, and then it worked great for her, but not for you. So, and then she calls you all the time. So the first thing is you don't answer the phone. Most of the time, she's gonna understand that no, stop calling, and it didn't work. So it's the same thing with that. You stop responding to the client. First signal, like maybe you should roam somewhere else. And the second threshold, the DOT is kind of the Dear John letter you send via email, of course, saying that it didn't work, I found someone else, or my ex came back. So those are kind of, I think, the feature that address your question. So on that, yeah.
So is there a lot of like, maybe you can explain some of the secret sauce that goes in behind, like on the controller perspective, that's helping this out? Yeah. Because it's not just the EPs, behind, right?
Because there's some logic on the EP, but there's some logic on the controller, especially when you can hear the client from multiple EP. So especially in a dance thing like that, when in the stadium where the controller knows better because the EP is looking at the client like in a straw, like he only sees that client and doesn't know what the controller there sees the signal, says that I know better. I know that life will be better with that girl there. I know your profile, like you should roam there. So that's where the logic, the secret sauce comes in.
And you're absolutely right. When we were doing a lot of the testing, we'd start at the network, hey, we're doing our comparison testing without with the RX-SOP. And clients, wherever we put them close to their APs, I mean, they'd associate to a lot of different people. I mean, client roaming algorithms are their own thing, and they would attach. Once you turn this on, they have to snap into the AP that you want them to snap in, the closest AP that they could do. So, I mean, that's a similar use case.
Good. Okay, on that I will sing something from Celine Dion.
No, please don't.
Thank you, JF. So I guess right here I was trying to point out that, hey, with our virtual contention cell, which is kind of set by our packet sensitivity, we have these very large listening areas for a bunch of cells that have small planned coverage area. So the blue is kind of the planned coverage area that we're shooting to hit for these cells. And because we didn't adjust the listening ability of our virtual contention cell, it's rather large, and it hears everybody. Like, so this 5180 kind of hears that 5180, and they share. I mean, you put these APs together, you want more throughput per square foot, and you don't get it because these guys are sharing the channel. So, and then the physical contention cell, which is set by -64, is a similar kind of a thing. I mean, it happens when you shrink the coverage plan size. So, I mean, this is kind of an ideal situation, a simulation-based. I mean, what we're trying to do is we're trying to make these large, obese cells, kind of shrink down to something more manageable that are kind of dedicated for their own cell and not sharing a co-channel cell a few cluster spaces over. So, and this is kind of real. I mean, this is like how big it is. I mean, this is your sensitivity of your radio, pretty much. So. So I wanted to show a plot of the general trends, okay? So we think, CCA, starter packet adjustment is something that's great. It can totally improve your network. What's the catch? And there's a big catch. There's a huge catch. It's a long rope and you don't want to hang yourself with it, right? So today we are over here. What I have is a kind of a trend line of throughput versus CCA and starter packet level. The smaller starter packet level over here, like the lower, I should say, the negative 100 range over here, kind of where we are today. We're sharing for a general trend of system APs. So this is kind of the sharing region where all these devices could be operating at a higher data rate if they were truly just limited by their SINR. However, they're sharing due to contention regions. So you start raising your SOP threshold. You don't want to be here. This is where we are today. You start moving it up a little bit. You get to the region where your cell, those big obese cells that I showed before kind of shrink down to what you're actually trying to cover, your planned coverage cell, and you're operating the devices closer to in your SINR region. So this is the sweet spot. This is where we want to be, right? I mean, we don't want to be. I mean, we don't want to be here because we're sharing and we're getting lower throughput. We want to be limited by what the actual raw data rate can do. Now, if you keep raising that, you got a problem, right? Okay, you got to this point where you hit your cell size, and you just kept taking it smaller and smaller, and wait a second, you got some coverage holes. That's a problem, right? This is where we don't want to be. Absolutely, you don't want to have coverage holes in your network, and which is why we've been very delicate about how we've handed this out in the past and how it's been implemented in the past, because. Again, it's a rope, and you don't want to hang yourself with it. So
you're saying I should go to the hospital and maintain tomorrow and just crank this thing up, right?
Just crank it up to -10.
There you go. Yeah,
you do not want to do that. This is on tape. I don't want to advise what.
But we should be able to see, as we start to tune this, channel utilization, right?
Oh, absolutely. Your channel is used. We were just talking to some of the stadium guys yesterday. A lot of there's 2-4 networks in stadiums. You're in a big bowl. Line of sight condition where you see, you can't separate things that far. I mean, you're in a stadium, it's a high density network, right? And you hear everybody. I mean, especially when the stadium is actually empty. And we have raw data of showing channel utilization, just turning this up a little bit. I mean, it goes from something like 40 to less than 5 or 10%. I mean, it makes a huge difference. We need this, in stadium and high density deployments, so. And it doesn't have to be just stadiums. Like I said, it's cubicle farms, lecture halls. I know we have a lot of deployments that take advantage of this as well. Anything where you're trying to shrink your planned cell size. So you just gotta scale things accordingly. Sir? I believe we're making it public on the 8.0 release. Is that true? Okay.
And it also exists in 7.6 today, right?
Pardon?
It also exists in 7.6 today at the CLI.
It is
available on 7.4. It's available on CLI, as even Jennifer tweeted that link about the core CLI commands. So that is available now. You can configure it. But from 8.0, we are putting it in the GUI. So even any user can basically try it out. You can just start with a highest value, then go to the medium and low. So you can gradually tune your network. So we are putting simple default, high, medium, low value from GUI. And that you can do it per RF profile based. So you can separate your, say, conference room area versus your hallways where you don't want RX-SOP. Or you can even apply globally. If you are just deploying for, say, one stadium, if you want to add that entire one RF domain, you can do that globally as well.
But when you say medium, high, low, what value are you putting to that? Is that something we can change and kind of start tuning? Like we start turning the knob and look at channel utilization, start turning to some more, start turning to some more. So
for expert like you guys, you can actually go into CLI and tune each and every value like next 75, next 74, next 73. But for the generic user, we have made that high, low, and medium value. Those are set for each radio. So I have one slide coming in which are giving you the exact NEC RSSI value.
Excellent.
But still you have flexibility to do each decibel, each interval value.
It's addicting, isn't it? It's crank this baby up. All right. But no, it's very helpful. It's very helpful in these networks. And again, our caution is you don't want to cause problems. So we need to be careful about that as well. Actually, what I mentioned before here is the general trend. You kind of see this cutoff region that I'm calling it, and then your SINR region, limited region, as well as your sharing region here. This general trend is nice, and why doesn't Cisco just turn this on? And why don't we just set some default settings for this for all cases? Well, it's highly dependent on your deployment scenario. How many channels do you have? How far are your co-channels spaced apart? And what kind of a network do you have? Is this an open field environment where there's a low exponential and path loss element? This was some basic simulation that we took early in the day, just trying to kind of predict kind of what we see based on like different kind of cluster sizes. 3-cell obviously being just for 2, 4, and 7 and 19. And the numbers at the side of it are just kind of numbers we put in there for an average exponential path loss. So the closer you get to 2 is more like free space. Anything more than that is, I mean, depending on what your network is, I mean, or not your network, but your environment is. If you have a lot of walls, obviously it's going to be a little bit higher than free space. But the key takeaway here is that, okay, well, we just can't pick a number, I mean, for an optimum cell size. It really depends on your network, and it's heavily dependent on your network. If you look at, I mean, some of the curves here, where you have a lot of separation in spacing between co-channels, like the 19-cell case, you can kind of see that you hit a max point a little bit lower, where you have the further separation, where you hit your max throughput point. And then you kind of start falling off. But I mean, smaller cells or cells that you have less path loss in between APs, it's a little bit of a higher level, and you don't get as much throughput as you wanted because in those situations you also are a little bit more SI and R limited. So it's highly dependent on the network, or your deployment, I should say, and it's not just a one-stop shop value that you could throw into every deployment and expect great results. So it's a tunable feature. I'll talk really quickly. I think we're running out of time here, but we have some data that we took like with a 19-cell cluster and a 7-cell cluster in an office environment, just showing where the client locations are. We ran them slightly 2 different frequencies just to get some adjacent channel numbers as well. So you'll see 2 curves here. But this is real data, okay? So we took the system throughput. This is percent of scalable throughput if all these were operating independently well. So this is the degradation we saw when we turned on all the channels at the same time. We're over here somewhere today with the sensitivity values. We started cranking up the CCA threshold for this cell for the 19-cell case. Eventually, you hit your SNI or SI&R range, and you're happy there. It stops there because we couldn't take any more data. We were cutting people off, right? And if we go to a condition where we're a little bit closer, we never really hit optimum SI&R range. We still have an improvement, but the channel, the network isn't, the cells are placed so close together that we do have a little bit more SNIR that we have to overcome, but there is still an improvement. So to wrap this up, 8 to 11 today. I mean, the CSMA is great, but you need to scale it for the deployment case. And with that RX-SOP and CCA is a means of doing that. But be careful, don't hang yourself, don't create dead zones. You could do that, and just use it with care.
So the question, like your question, George, so what are the values? So these are the values we have set. So we consider these values from many of our deployment in various stadiums or MWC or Cisco Live. So we are fixing this value for high, medium, and low. But still, we need feedback from you guys as well once you are deploying this feature. So what are the values? Whether should we add like more levels over here, like to adjust that value more flexibly? So we need feedback from you guys about that. But by the way, you can try this on WebGUI from 8.0 code, which will be shortly available, and it's available for beta. And before that, if you have 7.2 onwards, you can try this from CLI.
7.2 or 7.4?
7.2. And
in 7.2, it's not like if I go question my way through the CLI, it's not going to show up, is it?
It's kind of, yeah, it's a hidden command, but from 7.4, it's like you can just go and configure it.
Great, thank you.
And a couple of our like high-profile deployment, Mobile World Congress, Feb 2014 Cisco Live, which recently happened. And over here, we are deploying this feature, and we are seeing significant drop in channel utilization, sometimes even 20%, 30% drop in utilization.